Jai Hind all of you. I am Mohan Sharma, Assistant Professor from Ajay Kumar Garg Engineering College from the Department of Electrical and Electronics Engineering. In this video lecture, we are going to study about turbine speed governing system, and this topic is basically covered into the power system and operation control, and its AKGEC code is KEN070. So basically in this lecture, we are going to deal with, or we are going to study about the how frequency control is being carried out when load fluctuates, right? So basically we are going to study about the frequency control system in this video lecture. So let's start it. So firstly, we will have some introductory part. So under this introduction, yes, so we know that in the power system there is apparent power, right? And apparent power is basically comprised of two powers, that is active power and reactive power. And the basic function of active power is that the load is satisfied by whatever the load is there. Okay, so 90% of the load in the present scenario is inductive plus resistive load, right? So for functioning of the load, the real power is consumed, right? And for operating the machineries where the magnetization is there, magnetic power is there, so for magnetization your reactive power is necessary. So we see here that reactive power plus active power in combination works together to form apparent power. And we know that the power angle triangle is this one, in which we have S, this is the apparent power, right? This is 90 degree, and this one is reactive power, this is real power P. And we know that the unit of P is kilowatts and it is kVAR, and obviously this is volt amperes, or we can say that kVA if we are using kilos in the unit. This angle is theta, or sometimes it is also known as phi angle. So this is actually power angle curve or power angle. So if you know that you know P or you know Q, you can calculate S of the as that is the apparent power which is utilized into the system, right? So this is the power which is required by the load to function, and this is the power required by the machineries for generating the magnetic fields. Okay, so in the operation of power system, we know that both active and reactive power demands are never steady, and they continually change with the rising or falling of the load. So you know that whenever you for 24 hours load profile, you know that the load is not constant at any time, right? Load continuously varies. So if load is varying, so the impact of change of load comes directly onto the generation part, that is to the generator. We know that we have synchronous generators installed into the generating part or the power stations, and these generators continuously generates power, and the power generated must be equal to the power demanded, right? So power demand is basically the load which is connected to the system, and that load has to be satisfied with the amount of power. So basically if you are having, let us say, 500 megawatt of load, so you must have the 500 megawatt generation at least, and along with the load we have losses as well, right? So losses are there, and reserve capacity is there. So depending upon all the powers which are required at the load or reserve capacity for satisfying the transmission losses, so the amount of power that has to be generated at a power system or power plant is increased. Okay, so the PD, where PD is the power demand, let us say that PD is the power demand, and let us say that PL is the power which is satisfying the transmission losses, and lastly we can say that we have reserve capacity. So all these three powers must be, or we can say that summation of all these must be equals to PG, that is generated power, right? So generated power must be equal to all these powers. So in this way we can say that the power generation, or the power generation is basically, we are talking about the active power. So active power and reactive power both are not constant at any time. They are basically changing, or they are varying in a particular interval of time. So for our system to be under equilibrium condition, for efficient working of the system, your Pg must be equal to this, that is, this equation must be satisfied, right? So if we talk about the steam power plants, that is the power plants which requires steam to operate. Water input to the hydropower plants, so these are the hydropower plants which require hydropower, or basically the fuel is water over here. So hydropower plant or turbo generators, all these are basically works on the same principle of operation. Basically there is a generator which is connected to the turbine with the shaft, and in the steam power plants, steam is injected upon the turbine so that turbine can move, and in respect to that, turbine rotates the rotor of the generator. And if you talk about the hydropower plants, the water is injected with the help of a penstoke from a heighted portion, that is basically dam. So then this from this height, with the help of penstoke, the water is injected upon the turbines, and turbine rotates, and it is gonna connected with the help of shaft, with the help from the this rotor of the generator. So again it moves. So the far or less the operating principle remains same. So steam input to the turbo generators, water input to the hydro generators must be continuously regulated to match the active power demand, failing which the machine speed will vary with consequent changes in the frequency, which may be highly undesirable. I will give an example of 2014 grid failure. It was in 2014 or 2013. So grid failure was there. So you must be knowing about the northern grid, northern region or eastern region was completely under the blackout condition, and that blackout condition was the consequence of frequency disturbance, right? So a large portion of the load was disconnected from the system, and this resulted into a cascade failure of the systems, and one after other systems gone fail. And in this manner you see that the portion or large portion of the northern India was under blackout condition. So that was actually the case which was generated with the help from the frequency deviation, right? So we know that and this is the case that the maximum permissible change in the frequency is plus minus 0.5 hertz. So you know that in India 50 hertz is the frequency which is applicable all over the country, and the permissible change is 0.5 plus minus. So 4.9.5 to 50.5 is the maximum range. Above this and below this, the grid will fail. Then excitation of the generators must be continuously regulated to match the reactive power demand and reactive power generation. Otherwise the voltage at various system buses may go beyond the prescribed limits. So this is the case with the reactive power as well. So see, you must be knowing that frequency is there, real power is there, reactive power is there, voltage is there. So how you can control these parameters by frequency and voltage? See, real power is controlled by frequency control method, and reactive power is controlled by voltage control method. So in upcoming lectures I would be talking about the voltage control method. Basically that will be dealing with the controlling of the reactive power. Okay, so here we will talk about the frequency control method, and this must be regulated, or so that this basically finally this equation must be satisfied. This is the case. Now for small changes, active power is dependent on the internal machine angle delta. You must be knowing about this delta. This is the power angle, or this is also known as the load angle. It is basically the angle between the RMF and the actual rotor angle. Okay, so there is a little bit difference between the RMF and the EMF which is generated in between the air gap between the stator and the rotor. So rotor magnetic field is there and RMF is there, and the angle between them is known as delta, and this delta is about 30 to 45 degrees. This is the range of this angle delta. So this delta must be in between this range so that your system can be stable. Okay, now load frequency and excitation voltage control are non-interactive for small changes and can be modeled and analyzed independently. So basically we can see that our voltage control and frequency control, if the magnitudes are very much lesser, so we can have these control independently. There is one more reason behind this why we treat them independently, because see, I told you the frequency control and voltage control, they are two types of controllers. So voltage control is basically carried out by only machines, those machines or electronic devices, or we can say that the exciter is the device which control the excitation of the generator. So with the help of exciter we can control the voltage of the generation. And for this frequency control we have mechanical controllers. So we will be talking about the speed governor method in this frequency control method. And you know that governor is a mechanical device, and whenever they are mechanical devices, so mechanical devices are very much prone to losses. So the time period between the application of control part and the time at which the control is being executed, so there is a difference. So frequency control takes a little bit more time than if you compare to the voltage control. That's why we can have these controllers analyzed independently, right? So excitation control, see, we'll talk about this one. Actually this is the generator. See, this is our generator, and you can see that we have this generator connected with the turbine with the help of this coupling. Okay, this is a shaft. With the help of this turbine we can have our this turbine connected to the generator, so that its rotor rotates and the electrical power is generated. Now see, over here your turbine is being injected with the help of steam over here. Okay, this is the valve, and with this valve you can control the flow of steam which is being injected upon the turbine. Now turbine rotates with the omega, and same with the same speed this rotor rotates and power is generated and electricity is produced over here. Now see, if you have the control over the steam input to the turbine, you can obviously control the rotation of this generator, right? So this rotation is controlled, or this steam control is controlled by this valve. Okay, now we can see that the steam valve controller is installed over here. So this is actually controlling this valve, and this is the reference frequency and this is the actual frequency, and there will be difference between the actual and the reference frequency. So this controller will basically reduce the loss, reduce the error between both these quantities, that is actual frequency and the reference frequency. That is the basic case in which we can have the control over our frequency. So obviously this reference will be what, 50 hertz. Okay, and the frequency, this one will be the actual frequency which is being generated by the generator. Okay, now you can see over here, this is P plus JQ. This generator is generating apparent power. Now this from this portion we can see this one is the excitation. Okay, so from this we can see that our excitation controller is there, and this excitation controller is fed with the voltage sensor and comparator. Basically what happens over here, this is the voltage sensor. The voltage which is being generated by this generator is sensed by this comparator, and it works as a comparator in which the voltage is okay, see here the reference voltage is given over here, and from here you can see that this compares the actual voltage and reference voltage and generates the error. Now the function of controller is to reduce that error, right? Now this error is being reduced and this excitation will be controlled. Okay, so this portion from here you can see that this portion is basically dealing with voltage control and this portion is dealing with frequency control, right? So there are two types of control, voltage control and frequency control, and this voltage control controls Q, this controls P, that is real power, right? So excitation voltage control is fast acting, and in which the major time constant encountered is that of the generator field, while frequency control is slow. That's what I just said you. This excitation voltage control is fast acting because it has time constant and the values of those time constants are very much lesser. Why? Because this is some only electronic devices, but here we require mechanical devices, right? That's why the time constant difference is there. Now Thus, time constant is much larger than that of the generator field. Thus, the transients in the excitation control vanish much faster and do not affect the dynamics of the power frequency control, right? So there are this moment of inertia. Whenever mechanical device is there, mechanical motion is there, you will deal with moment of inertia, right? Now, the controllers are set for a particular operating condition, and they take care of small changes in the load demand without frequency and the voltage exceeding the prescribed limits. So this again, here we will be having some range in which the in that range the operation of your this controllers will be carried out. Okay, so outside this there will be no frequency control, or if the value is exceeding beyond this limit, so there is a need of control your frequency. Now, with the passage of time, as the change in the load demand becomes larger, the controller must be reset either manually or automatically. So controllers are also devices, controllers are also machines. So whenever there is a passage of time or a large operation, large for very much larger time, they are continuously working for a long durations of hours, so ultimately they have to be reset at a particular moment of time. That is, it can be either manually or automatically. Okay, so this is the controller part of the general controller part of the machine or this power station, power generator, where voltage and frequency control is carried out, right? Now we'll talk about load frequency control. So load frequency control is very much important over here. So we will be dealing with single area case only. So there are two areas, okay, multiple areas are there. So we will firstly deal with single area. Now we are just considering a problem of controlling the power output of a generator of a closely knit electric area so as to maintain the scheduled frequency. So what we are doing, we are having area, okay. So in this area, let us say this is area A1, and in this area we have a generator, we have some load connected in this area. So for this particular area, you have generator of closely knit electric area, so that we have to maintain the schedule, we have to maintain the scheduled amount of frequency. Okay, now all generators in such an area constitute a coherent group, so that all the generators speed up and slow down together, maintaining their relative power angle. Such an area is defined as control area. So this is basically the control area. This is the control area over here. And if you are having a number of generators, let us say there are 3 generators or 4 generators, so they all have to work in a unison. Okay, so these are some basic rules, so that you can control or you can operate these generators in parallel as well as in synchronism, right? So if they are increasing their speed, all the 4 generators will increase their speed at the same time. If they are decreasing, they will decrease at the same time. Okay, so the boundaries of a control area generally coincide with that of individual electricity board. This is something other things, that is basically we are talking about the if this one is a second area. Okay, so this is area 2, so we are just talking about these boundaries over here. So to understand the load frequency problem, let us consider a single turbo generator system supplying an isolated load. So the system is just like this, and see, this is speed governing system. So firstly you must understand what are the devices or what are the components which are connected over here. So firstly, you see, this is the opening of the valve from which the steam will be coming out to the turbine. So here the turbine is connected. So on this turbine, this steam is injected from this passage, right? And steam is input over here, which is coming from the is boiler. Okay, so boiler will be there, superheated steam will be there. So from there steam will be coming, and from that this steam will be coming into this passage and coming out of this area. Now you can see here there is a valve. Okay, so here you can see there is narrow opening, and this portion, this valve can be moved up or down, so that the valve can be opened or closed, and accordingly the steam could be controlled. So that the amount of steam injected on the turbine is sufficient, so that a particular so that it can be it can rotate at a particular rotation or at a particular speed, right? Now this valve is connected directly with the main piston of hydraulic amplifier, that is basically the speed control mechanism. Okay, now this hydraulic amplifier, what is this hydraulic amplifier? Basically there are two valves over here. You can see this is the first valve, this is the first valve, and this is the second valve. Okay, now what is the function of these valves? See, this is the main piston. You can see over here, this is the main piston. This main piston can move up and move down over here. So you can see if this piston is moving upward, so the area is becoming narrow, and when area is becoming narrow, you can see it will close it. Okay, when this piston is moving downwards, area is becoming broadened, and this will open the passage so that a high amount of steam could be injected. Now see, there are linkages. See, these A, B, they are known as linkages, right? Now you can see these A, B, C, D, E, they are pivot points. So pivot is basically the point at which, from which this can be rotated. Just like if I say this point is pivoted over here, so from this point it can be let us say it can be, if this is pivoted, so it can rotate like this one. Okay, so one portion is fixed and other portion can be moved. So these A, B, C, D, E are pivoted points, right? Now you can see there, if let us say that C, or we can say if D point is pivoted over here, so if this point is fixed, you can see this portion can be moved upward or downward, right? Now there is a pilot valve over here. Pilot is basically the one who rides, or who actually rides the car, or someone who is the basically who is the rider. So the pilot is over here. So this is the valve. So you can see whenever this D portion, direction of the positive movement is taken as, so basically we will deal with this one direction as well. So downward direction is taken as positive, upward direction is taken as negative, right? So let us say that the direction of the positive movement is downwards. So if D moves downwards direction, so how, firstly we are talking about how this main piston will work. See, if here, from here, high pressure oil is injected over here. Here is high pressure oil is injected. Now you can see that this portion is filled with high pressure oil over here, and this over here, this one, this is filled with high pressure oil, and you can see that this portion and this portion are completely blocked by the valve. Now if this valve or this D portion moves, let us say the firstly downward direction. If D moves downward direction, what happens? If D moves in downward direction, the portion which will be covered will now become this one. Okay, so this will be the valves, and you can see here this portion will be opened. Now if this portion is opened over here, the high pressure oil will move in this direction and force this main piston to move upward, and when this moves upward, it will close the valve, right? Opposite to that, whenever this portion this portion or D portion moves upward in upward direction, the position of the valves are this one, and you can see over here this portion fills with oil and the oil moves from this direction. Now when oil moves from this direction, it will exert a force from upward from this direction to the main piston, and the main piston starts moving down in downwards direction, right? So whenever there is a downward direction force on the downward direction, you can see this valve moves downwards and it opens up. So whenever it opens up, the high amount of or more amount of steam can be injected to the turbine. Okay, now this is one criteria by which you can control the flow of this steam, right? So this is one criteria. Second one is we can say that this is the manual operation. So how the manual operation can be carried out? See, here are speed changer unit. This is speed changer unit, and this speed changer unit, basically with the help of this speed changer unit, you can see this is for lowering the steam flow and this is for raising the steam flow. Now you can see over here this is controlled by a speed governor. right? So most of you must be knowing about the speed governor. What is basically one speed governor is? See, speed governor basically operates on the principle of centrifugal force, right? So if I take an example, let us say that we are having a pendulum, right? So you are having a pendulum, and pendulum is suspended like this one. Okay, so this is the pendulum by which it can be moved. Now if you say that you are having a suspended pendulum, and if you start rotating it, okay, with the help of little force, if you start it, when the rotational motion is lesser, you can see that the position of the pendulum is quite lower. Okay, so position of the pendulum will be over here, and if you are rotating it with the help of with the very much lesser velocity, it will rotate over here only. But if you gradually increase the speed of the pendulum, and it will start from coming from this position to this position, up. So if you increase the speed of the rotation, so the ball or the pendulum which is suspended into the air will move upward. So centrifugal force is taking that pendulum to the upside direction. Basically we can see that this is the tangential direction. So this is acting just like a pendulum over here. So just like over here, so this portion moves in this direction, and this is fixed over here, and you can see that these are the two balls which rotates or in a very high speed or lower speed. Whenever the speed is higher, these two balls moves upward. Okay, so basically it not move upward, it moves in the outward direction when it moves with the higher speed, and when it moves with the higher speed, it will move apart, and this will drag this point B downward direction, right? So when this point B will be in downward direction, similarly it will control the operation of this valve. Similarly, if this I'm taking the next red yellow pen, if this is in this direction, okay, so if speed is lower, so when speed is lower, these balls will contract, and accordingly this portion B will move in upside direction. So whenever this is the upside direction, it moves in upward direction, there is a change in the position of this valve. Okay, so this is how your speed frequency turbine of speed governor of for controlling the frequency works, right? So there are fly ball governor. So what fly ball governor does? So it is basically the heart of the system which senses the change in the speed, and the fly ball governor which we were talking about, the balls were there. So that is basically the fly ball governor, and it is the heart of the system, and it senses the frequency change, right? And as the speed increases, the fly balls moves outward, and the point B on the linkage mechanism moves downwards, right? Now the reverse happens when the speed decreases. Now we have hydraulic amplifier. Now the work of the hydraulic amplifier is just like I told you about the main piston. So hydraulic amplifier consists of a pilot valve is there, main valve, main piston arrangement is there, lower the pressure level pilot valve, moment is converted into the high power level position, piston valve movement. This is necessary in order to open or close the steam, while steam valve against the high pressurized steam, right? Now linkage mechanism is there. So whatever the position which are connected between A to B, B to C, C to D, they are basically linkages. So A, B, C is the rigid link pivoted at B, B is the pivoted point over there, and C, D is another rigid link pivoted at D. Now this link mechanism provides a moment to control valve in position to change in speed. It also provides a feedback from the steam valve movement, that is link number 4, right? Now lastly we have a speed changer which was connected to the topmost left corner, and it provides a steady state power output setting for the turbine. Its downwards movement opens and upper pilot valves so that the more steam is admitted to the turbine under steady state conditions, right? So hence more steady power output can be taken care of, and the reverse happens for the upward movement of the speed changer, right? So this is all about the speed speed governing system. And lastly I would like to show you the block diagram of the complete system, right? So I'm skipping this. this is the complete block diagram for representation of load frequency control of an isolated power. Here you can see that there are 3 blocks. First is for speed governor. This is the block diagram for speed governor. This is block diagram for turbine, and this is for the complete power system. Here the delta F is the change in the frequency, and accordingly the change in power is carried out. Okay, so this is the diagram or block diagram through which this control action can be, frequency control action can be carried out, right? So this is all about this lecture. Thank you very much. Jai Hind.